Okay, given a line segment AB with length 1 for any n in the natural numbers, construct a line segment measuring 1 over n and square root of n. So that means, well, before we look at what that means, let's interpret this. This symbol right here is the universal quantifier. It means for every or for any. And we're going to use for any because every n, we don't have the time, we don't have the paper, you don't have the pencils to do every n. So we're going to show for any n. That's good enough. For any n, we're going to show that we can construct a line segment measuring 1 over n and square root of n. If we can do that for any, then it's just like doing it for every, we'll say. So that's the challenge. Given points P and Q, with PQ being unit length, construct a line segment measuring 1 over 4. 1 over 4. Okay, let's can do. All right, here we have P, and here we have Q. And we want a line segment that's 1 over 4. And we're told PQ is unit length. So that means this is 1. Length 1. So here we go. First thing I'm going to do is divide this in half. This just needs to be a little bit more than halfway. I don't have to know exactly where halfway is. I just have to know approximately, and then just go a little bit more than that. I need a little bit more than halfway because I want these circles to cross. I'm going to draw an arc above, an arc below, just enough of an arc in the spot where I think, and then I keep this thing the same. This has to be, do not move this distance. Keep it the same. Go over here to this end. Mark there. And then mark there. And once you've done that, connect these 2 points, meaning this one here, these intersecting points. Those 2 points are on a bisector, a perpendicular bisector of PQ. So that is halfway. So I want to find a point, a midpoint between here and here, and we call this R. This point. So this is 1/2. So let's just do that again. So P to R. I want a little bit more than halfway. I make my arcs like this. I have another perpendicular bisector, and this perpendicular bisector goes through the line segment at a point S, or T, or W, or whatever letter you want to call it. PS, that's equal to 1 over 4. Now, I think you can see that using these perpendicular bisectors, this method, we could get a line segment that's 1, well, here's 1/2. This is 1/4, right? That's right here. That's 1/4. We could find a perpendicular bisector between P and S. That would give us a line segment that's 1/8. You'd do that again, get a line segment that's 1/16, 1/32. But how would we get a line segment that's, doesn't have anything to do with the power of 2? Okay, well, we've done this. This would be n equals 4. But we know we could do n equals 8, n equals 16, n equals 32. We could find 1 over n for n equal 2 to the k, say. All right, that's the first challenge. Okay, here's the next challenge. Given points G and H, with GH being unit length, construct a line segment measuring 1/3. Okay, so, and we're constructing using only compass and straight edge. There's a straight edge. And no, cannot measure here. Divide by 3, that's cheating. 1/3. So this is 1. This length is 1. I don't know, maybe it's 27 light years or 3,482 kilometers or 7.5 miles, 3 inches, whatever. We're just going to call it 1. And we're going to divide it into thirds, or we're going to find 1/3 of that length. Ready? Okay, here we go. All right, we just need another line segment. We're going to draw a line, maybe say off from G right here. And could go any length. Draw it long enough like this. And again, this could be any angle, any random angle at all. Okay, once you've got that done, and you take the compass, and you're going to make 3 points. You're going to mark 3 points on this line. 3 because we want thirds. This is what we mean by any n. If we want 1/5, we'll make 5 points. If we want 1/7, we'll make 7 points. If we want 1/9, if we want 1/29, we'd make 29 points along this line. And so I'm just going to set it to, I don't know, some distance like so. And I'm going to make 3 points, mark 3 points on this line. Now the way I'm marking these points, these line segments, the distances between them are the same. Distances between these points are the same by construction. Right? These are all the same distance. So here I have a line segment here, and I've got 1/3 of that. Exactly, don't I? Okay, so here's the trick. Draw this line segment to H. Goes through here. Like that. And I'm going to put this, I'm going to make this, oops, that's not long enough. Just going to make this a different color so it's easier to see the marks, that they're separate. Okay, so I got this connecting that. Now what I want is I want to copy this angle that's right here. I'm going to copy that. This angle. That angle right there. Copy that angle. Ouch, I poked myself. Careful with the compass. These things can be dangerous. So I'm going to copy this angle like so. Yeah, just make these marks with that arc. I'm going to go to here. I'm going to draw a similar arc. And then from this point, I'm going to put the compass here. And now I change the distance because I want it to reach where it crosses here. All I'm doing is I'm duplicating an angle, cloning an angle here, and you will do the same thing over here. Just like I marked that across that arc, I marked in a similar fashion, like that. So I have this point here, don't I? And I'm going to draw this line segment from here to here. Oops. Like that. Now, what do I have here? I have parallel lines. This angle, if you look at it this way, we have two lines, two coplanar lines, and here's a transversal. The orange is a transversal. This angle is congruent to that angle. These are special angles. These are special angles. If you want to say alternate interior, then from a vertical angle, you have that. They have alternate interior angles. But these congruent to implies that these lines are parallel. Now, if I did the same thing here, just imagine I copy the same angle. I'm not going to, but I could. So if I cut that right there, I would again have another parallel line. So I'd have these parallel lines and a transversal. These lines cut by this transversal, they form congruent segments. Parallel lines that cut a transversal into congruent segments. Those parallel lines cut every transversal into congruent segments. That is a theorem that has been proven. So I'm on my way, right, to getting all these parallel lines. But I know that if I draw this next line, I'm going to have these parallel lines, do the same thing along here, copy that right there. I would have all these parallel lines. I'd have 4 parallel lines. And these 4 parallel lines cut by a transversal are cutting that transversal into 3 equal segments, 3 congruent segments. If the parallel lines cut the transversal into equal segments, congruent in length, then every transversal across those same parallel lines are cut into congruent segments. So all I need to do here, label that point H, I don't know, call it K. KH. That is equal to 1 over 3. Now, if I wanted to make a segment 1 over 5, I would have to divvy this up into 5. Well, I actually don't divide this. You have to just make something that's 5, length 5. Because you aren't going to know. So you need the whole line. Draw this entire line. And then just choose randomly. It could be any length at all. And if you want 5, if you want 1/5 out of this, then you need 5 chunks, 5 distances going across this way, 5 times. If you want 7, if you want 1/7 of this line segment, then whatever you choose, you keep it that way, and you mark. You mark it 7 times. First, you want to choose a distance on your compass so that you don't run out of paper. So KH would be 1 over 3. Okay, here's the final challenge in this mini series of constructions. Given points A and B, with segment AB being a unit length, construct a line segment measuring square root of 3. Okay, this will be done using the Pythagorean theorem. And we can do this for square root of 4, which is just 2, pretty easy. But square root of 5, square root of 6, square root of 7, square root of 8, you'll see how we can construct a line segment measuring the square root of those natural numbers. So first thing we need to do here is we need to extend this line segment because we want a perpendicular going through the end. Could be either end. We'll choose B. Okay, so we'll make perpendicular going through B. And so that means we just can mark here, mark there, like so. Perpendicular through B. So this video is not teaching you. This video is not teaching you how to make the perpendiculars. It's not teaching you how to bisect angles or even duplicate an angle. It's not the goal. You can find another video for that. This video is teaching you how to construct segments of any fractional length or segments of any square root of a natural number length. So here we have this point over here in space. We could continue this line like we did. We can do that because of continuity axioms. We have a continuum, infinite points. We have a line segment. That line segment is part of a line. We have infinite points past the ends. So here we have our perpendicular. There, very nice. Okay, we're using the Pythagorean theorem, so I'm going to make this, copy this distance right here with your compass. Because we're told that's 1, so let's make this 1. So we know this distance here, that's 1. Right there. Because this is 1, and this is 1, we know that this line segment here is like the diagonal of a unit square. This thing is square root of 2, isn't it? If you don't know that square root of 2, then you need to stop this video now and convince yourself of that with something. Okay. So we have our square root of 2. How do we get square root of 3? Well, let me just extend this. And here, let's do the same thing we did before. Let's put a perpendicular through this point in this line, like so. We'll do it by we can make the mark on any side of it. Make it over here, just so it's kind of out of the way. So there's our point for the perpendicular. This line here, that's perpendicular. Now let's again make side 1. I use Pythagorean theorem again. So we'll mark this. Here's our length 1. Now we'll connect these 2 points here. This is 1. This is square root of 2. Here we have a right trigon. Right trigon. With a leg that's square root of 2 and a leg that's 1. Let's call this, give it any name, call it Q, that point there. AQ equals square root of 3 by the Pythagorean theorem. Right there. Okay, here we go. Given points P and Q with PQ equal to 1, construct a line segment measuring 2/5. 2/5. That's what we're going for. All right. So any angle at all, but you want to give yourself some space to make the constructions. You don't want to run out of paper. You want to be able to swing your compass comfortably. So choose based on that. I'm going to choose something like this. There's my line. I'll make it orange. Okay, so somewhere out here, there's going to be a 5th dot. I'm going to make 5 points. Mark 5 points along this line. And they're all going to be the same distance apart. Maybe I should fix this better. Okay, here we go. You ready? We got to make 5. Whatever this is, it doesn't matter. Does not matter. You just don't want to run out of paper. Denominator is 5, so I'm going to put 5 of these marks, equidistant points from each other here. 1, 2, and there's 2. There's a 3rd point. Here's a 4th. And there is a 5th. Oh, I went right to the end of it. Just like that. Okay, so I connect this 5th point in Q with the end over here. I'll use the non-marked edge. There we go. Now, this line right here that we connected, we want parallels to this. To get parallels to this, we need to copy this angle here. Okay, so let's do that. And this is not about copying angles. You learn that somewhere else. Let's see, we'll go like this. Make an arc there, like so. And do the same thing. I keep that same distance. Make a similar arc. Come over here, make the similar arc. I could do that all the way. I don't need the lines over here, but I'll make them anyway. Or I'll be prepared to make them. So these are all, those are all the same now. I'm just gotta get this distance from this original angle that I'm copying. Get that distance. Like so. Once I know that distance, then I come over here and I mark that distance there, mark it here, mark it here. I would mark it here. Okay, those are the points I need. Now look, if I draw this, that point to this point, those 2 points, if there are any 2 points, you got a line. So if I do that, there's a line. I can connect these two here. There's another line. Here's another. And another. So I got that thing divvied into fifths. Right? Because, look at these here. Let's call this angle, we'll send this is going this way. So this angle here, call that alpha. Well, that means that this is alpha because I copied it. Which vertical angles, there's alpha. So you can look at it that way if you really want to see alternate. If you want to see alternate interior angles. But these are also special pairs of angles. And they're congruent. These are corresponding angles. And they're congruent. Corresponding angles that we get from a transversal that intersects 2 coplanar lines. So we know these lines must be parallel. And the same all the way through, right? All of these lines have to be parallel. They must be, because we have these corresponding angles congruent. We also know that these segments are congruent. They're all the same length. We constructed them that way. So here we have a set of parallel lines intersected by this transversal. And these parallel lines, they cut this transversal into congruent line segments. That's what these parallel lines are doing to this transversal. That means they do it to every transversal. Every single transversal across these parallel lines will be cut into congruent segments, as they did right here. So that means, how many segments do we have here? 1, 2, 3, 4, 5 segments. We want 2 of them. So let's call this point, I don't know, call it T. Call that point T. TQ. Measurement of TQ is indeed same as 2/5.